So I'll cover kind of two main topics. One is an overview of the NRC licensing process. In the alphabet soup of reactor licensing, by the end of the talk, you should know what 10 CFR 50 is, 10 CFR 52, and the GDCs. If you don't, then I probably haven't done a very good job. But I'll try and avoid as many of the acronyms as I can. I'll talk about, in particular, about examples of pre-application regulatory activity. This is going to be the most important period, especially for any kind of new innovative technology, because it's a period where you can get the most leverage out of interaction with the NRC to set you on the right course so you don't have to go back and make big corrections later on in the process. So I talk about a few examples there. Then I'll talk a little bit about some current activities to support advanced reactor licensing. This is really an open topic. We're not sure how things are going to go exactly, but it's exciting that there are a lot of people pushing and kind of testing the waters to see progress in terms of clarity in the process and make it more transparent and more efficient. I'll talk a bit about the general design criteria, which are part of the federal regulations. They are light water reactor specific. There's a process to make them applicable to other technologies as well. But that's really the main source of where a lot of the safety requirements in design come from. And even if a specific requirement doesn't apply to a reactor technology, you still have to go through the process of understanding the basis for that safety feature and why it may or may not apply to any kind of new innovative reactor technology. And then hopefully we'll go through a little bit of an example of design questions that come up as a result in kind of fishing through the regulatory process of kind of trying to understand how you can make different design decisions based on regulation. So it's important to note that the current framework we have for nuclear and safety licensing has evolved from a historical experience base where there was no previous experience, and going all the way back. It seems like the slides are a bit cut off, so there are references on some slides and titles on some slides that'll be cut off. So this is CP1 in Chicago, and it's important to note that from the very beginning, people knew that designing reactors would require certain safety systems, in particular reactivity control systems. And so a lot of this was done originally in kind of an ad hoc basis, but safety was very much a concern, although it was implemented very differently than it is today. And it's also important to remember that there was a period where we didn't have an existing fleet of light water reactors and a broad set of regulations governing how things done. There were original prototype plants built for light water reactors. They were done very much in kind of an ad hoc and a testing basis, but the designers knew that safety was an important part of that process. So let this be, I think, a symbol of hope that there's a way to get through this, and we've done it before. We've gotten into a place where there are a lot of very specific requirements associated with the existing reactors, and that may make it hard to see how to do it again with new reactors, but I think there are a lot of people that are hopeful that we can do that. All right, so a little bit about the licensing process, and there's going to be a lot of content on the slides. I think a lot of it will be useful for reference. If there are any questions, I'm happy to discuss parts in particular, but I think this will give you a framework of how the regulations are structured, where they're described, and if you have specific questions, it'll be good to go back and reference different parts of the process. There are other sets of documents that I don't talk about here, but if you have questions, I'd be happy to respond by email or in person. So it's important to start first with the Code of Federal Regulations. So it's important to note that the Code of Federal Regulations, the CFR, is law, and the NRC does not actually have authority to waive requirements of the Code of Federal Regulations. So there are parts where there are exemptions that can be made, but basically this is law. So if you don't follow it or don't have a very good reason for an exemption, then the NRC can't do anything about it because it's not up to them to decide, essentially. Title 10, which is usually the prefix, refers to energy, and there are a few different parts that are important to nuclear reactor licensing. Part 20 is for standards for protection against radiation protection. This is more for plant staff and operations. It sets dose limit for personnel. Part 50 is the two-part licensing process, which has been used for all of the currently operating reactors in the United States, but is not being used now, and actually it's uncertain whether the NRC actually has the internal capability to review a Part 50 license application if it was submitted today. So that's important to consider. Part 52 This is often referred to as the combined licensing process. So it's a one-step process. I'll describe that as well. And this is the process by which the current plants in Georgia and South Carolina are being licensed and built. And then I'll make a note here that it's not just a reactor design that you're working for, it's a site, and the site has requirements as well, and those site requirements are in Part 100. In terms of site restrictions, I'm not going to dwell since a lot of them have to do with the details of the local geography, the local soil, a lot of seismic issues and kind of external hazards. But in general, when thinking about sites, there are different zones around the plant that you have to think about. There's an exclusion area, which is basically the owner-controlled property, which is if you don't work for the plant or supervise, then you can't access that. And those have dose limits associated with accidents. There's a low population zone around the plant, which basically is public access, but you want to limit any effects of public radiation releases in that zone. And then there's a population center distance. And all of these guidelines are set by basically 1,000 megawatt light water reactors. And so you have to plan for large emergency planning zones based on a light water reactor. And it's really important right now that small reactors like NuScale are working through the process of how these change when you scale down your power level. You scale down your thermal core power and your source term essentially. So the threat or the challenge changes as reactors change, and so these are somewhat in flux. I think a pretty common goal for most advanced reactors is to basically make the exclusion area and the low population zone the same. So essentially there's no limits on population outside of the property that's owned by the plant. That's a goal of multiple advanced reactors. So this is 10 CFR 50. This is the two-step licensing process. So there are a variety of reports that need to be developed. Most importantly is the preliminary safety analysis report, which has a wide variety of content describing the plant, its response to different safety challenges, and the design features of the plant. That is reviewed. There's feedback from the NRC. There's public hearings. There's additional oversight and review. At the end of that process, you get a construction permit, which is basically allows for pouring a first nuclear concrete. But the thing is, when you go through that process, you begin construction and you build the plant, you have to go through another final safety analysis report, which basically gives you the operating license. So it's a two-step process. I'll compare a little bit of the advantages and disadvantages of this, but this is how historically all of the operating reactors in the United States have been licensed. It's important to note that the last construction permit was issued in 1978. So this is a regulatory machinery process that has not been fully utilized in quite a long time. And instead, so there were issues with the fact that there's a lot of risk in going through the construction process and not having the confidence of whether you'd be going into the operating phase. I grew up in Long Island in New York, not too far from Shore Plant, and that is exactly the model of what you don't want to do, where you basically build a plant to completion and you lose all the investment and you don't get to move forward and operate it. So that was a real danger of this licensing process. It motivated a lot of the purpose behind going to a one-step licensing process, and that was developed in the 90s as 10 CFR Part 52. And essentially, the process works. It's a bit more work on the vendor side up front is the key. So I tried to note in this slide kind of who does what in the licensing process and at what stage. So the important thing is that it's the reactor vendor, it's the Westinghouse, the GE, Areva, who submit design certification application. They get general design certification on a design, and that approves a generic reactor plant design. It's approved for a generic site, but it's not specific to any site that a utility may want to build the reactor. So utilities will then go through the licensing process for a specific site, including early site license, and they'll ultimately obtain the combined license for construction and operation of the plant. And they'll do this with a lot of support from the vendor. It's in their interest to support that process. But it's the utility who submits the license application. They hold the license. They're the owner and the operator of the plant. They hold the license. So the process that we're working through now, or will be working through, is that after you get the combined construction operating license, you have to go through this process of inspections, tests, and acceptance criteria, ITAC, to basically prove that the as-built design matches all of the specifications in your certified design, and then you can go forward and start operating. This is a process that there's a lot of uncertainty because it's never been done before. Vogtle and Georgia will be the first to work through this, and the expectation is that they will, but the process is not really fully defined at this point. So again, this is Vogtle, and so 10 CFR 52 is currently being used by the NRC, and the expectation is that any new, at least light water reactor application will go through Part 52 with the NRC. So I already mentioned a bit of these in passing, kind of advantages and disadvantages of Part 50 and Part 52. So the major advantage of Part 52 is that it allows you to get started with construction earlier. You don't have to have as complete of design, and it gives you more flexibility. If you discover things as you're building the plant, you can make modifications on the fly, essentially, and you have to assess whether they're important to safety ultimately, but it's not going to change what you submit ultimately in the final safety analysis report because it's part of the process. With Part 52, if anything you do in construction deviates from the certified design, it can be a major process to go through and revisit that question and assess whether it's important to safety, and something you have to do in the moment rather than doing as part of a final safety analysis report. The big downside of Part 52 is it requires a lot more detailed design of the reactor up front. It's a lot more expensive to develop that, and there's less flexibility if you discover things during the construction process that would be good to change. So in the advanced reactor space, there's a possible alternative path, and it's possible to do prototype licensing under Part 50 and Part 52. The issue is that the NRC has never licensed a prototype plant before, and so while this regulation exists, the details of how you would work through this process have never been defined. And this is a topic that's come up as something that's particularly important for any kind of non-light water reactor technology. And so I'll go back to the Code of Federal Regulations. So there's a definition of prototype plant, and basically it describes what you would expect as a prototype plant with the condition that it may include additional safety features to protect the public and plant staff from possible consequences of accidents during the testing period. So this process is untested, and nobody really knows what additional safety features the NRC would actually require. And it's not until someone actually try and exercise this process. There'd be a lot of probably commission review and policy making, and generally there's no advantage of being the first applicant to go through that process. Everyone will want to be second once the process has already been worked through. Yeah.
NRC never licensed prototype plants. That's surprising.
It's only because the NRC was formed in 1974. So all of the unusual experimental reactors that we built in the United States were licensed by the Atomic Energy Commission. And there were a lot of them, many of them at Idaho at the test site. The NRC did have a little bit of overlap with some commercial prototypes of non-LWRs, Fort St. Vrain being kind of the main one. So there's a little bit of experience early on. They also have completed preliminary safety evaluations for a few other advanced reactors, PRISM and the modular H2GR being the two main examples that I would reference. But no, there hasn't. Basically, by the time the NRC came around, we had already started building most of the fleet in the United States, and so the real focus of the NRC has been on regulating the existing reactors.
But those paper records must have been written down somewhere. The lessons learned in that process last time.
It's mixed from the AEC days. It's not as well documented as a lot of the more recent activity from the NRC.
You're saying everyone wants to go second in the queue, then surely no one's going to take the plunge and go first because they're not sure what's going to happen with regards to regulations. So that thwarts innovation right there. Sure.
Yeah. So if you want to do a prototype plant, you have to have a really good or clever approach for meeting this requirement for additional safety features. And ideally, you want to do it with minimal changes to what you would expect in your commercial prototype.
Where do you think that, so like if someone is taking the plunge, who do you think it will be? Will it be through a government, like at a national lab or something, or like a university project, or do you think it's possible to be done
I think ultimately the federal support has to play a role in a prototype plant in the United States. Yeah.
How different this is with the Part 50 and Part 52? Because these 10 positions will be used to use the prototype plan for the generation 4 reactors. But in the end, still have to get the proper licensing for the real commercial.
Yeah. So my understanding that both Part 50 and Part 50 and Part 52 have a lot of the same structure and provisions. There are differences in the details of what you need to produce at different stages. My understanding is that the prototype provision applies to both Part 50 and Part 52. So if you are really confident in your reactor design, you can go for a Part 52 prototype plant to get your construction and operating license. I really doubt that a Part 52 prototype plant licensing application is going to be successful. I think it's you're shooting for too much too early. But I think in terms of the law, the pathway exists. I won't go into it here, but there's a bit more detail on test requirements on what a prototype plant would need to demonstrate, or what you could just demonstrate through alternative testing to support licensing. This is in NuScale 50.43. But this includes pretty much the same provisions as the definition, which that there be additional requirements, and these requirements have not been defined. So the title of this slide is Contents for a Safety Analysis Report for Part 50 or Part 52 applications. So the question is what do you actually have to do to submit a license application? And so these are essentially the chapters of a license application. And for light water reactors, there's detailed kind of sub-content that has to go into each of these chapters. You'll produce many thousands of pages of reports that will be submitted to NRC. The review will be approximately 4 to 5 years if everything goes well. So this is a huge amount of work to go through this process. If you're looking at a new technology that's vastly different, you don't want to start off saying, I'm just going to do all of this. You have to strategically pick the areas where you have the greatest risk in the process and address them early, and then you can go back in and add the detail that you need once you're certain that you can get through the process. So, but this is really a wide scope of what you need. The level of detail depends on what license path you ultimately pursue, but it is kind of difficult to grasp the huge amount of work actually required to get a license application submitted. It takes a long period of time just for the NRC to determine if a license application is complete and can be reviewed. It's not a trivial process. So when you go through this point, you really want to be confident that you have a high probability of success. The problem is that in the current licensing framework, you have to go very far to achieve that prospect of success. And many advanced reactors have kind of started that process and stalled out and not made it through. And another important reference, and this is useful for advanced reactors as well as think about scope, is New Reg 0800, it's a standard review plan. This is guidance to the NRC staff on requirements for adequacy of all the different parts of the license application. And so there are parts of this new reg for each chapter, and there are subparts, and there are subparts that are specific to PWRs and BWRs, but it's all light water reactor focused, and it's all geared towards large light water reactors because those are the only applications that the NRC has historically received. There has been a process to develop design-specific review plans, first for mPower and then for NuScale, and so these are cousins of essentially the existing standard review plan, but they're revisiting some of the requirements for large reactors, looking at multi-module requirements, staffing, shared systems. There's a whole set of issues that the small modular reactors have to go through that will be applicable to advanced reactors, and so it'll be interesting to see how those design-specific review plans come through the process. So I guess an important point is if you're thinking about a new reactor technology, you don't want to have to do all of this from the very beginning. So it's important to recognize that there's actually a period of pre-application engagement with the NRC. I think the thought is that your first meeting is free, but then you have subsequent meetings where you pay the NRC staff fees. And my understanding is that it's not actually the staff fees that are the major constraint to the investment of kind of getting through. It's all of the investment in the R&D required to address the staff issues in that process. And the risk is that you don't really know if how the staff is going to respond once they receive the entire application package, and you don't know how the commission is going to respond. It may or may not actually agree with the staff's opinion. So this is a really important opportunity to test the waters and to achieve a lot of important things. So I think every pre-applicant has gone through, has recognized that it's important to address the really big pitfalls in this process and at least get a sense of what they are. There are a number of other objectives, so it's also important to describe and just present and familiarize the NRC staff with your specific reactor technology. The NRC staff is very familiar with the existing light water reactor fleet. It's going to take them time to understand reactors that have different safety features. It took a long time to understand just the change from active safety to passive safety with our current plants. So you can't just expect that you can show up with the best gadget reactor design. The NRC will say, this is great. It takes time for them to understand really the details of technology, and they have to understand it in a way that they can probe areas and question. So they take that learning process very seriously. There's a process of going through and identifying all the applicable regulatory requirements. There are many thousands of specific requirements, and it's important to work through and understand which ones may or may not be important for your reactor design. It's important to assist the staff in resource allocation. So the NRC is a bureaucratic agency. They have to plan budgets on an annual basis, and they have to know how much staff has to be devoted to different parts of the process. If you don't let them know what your schedule is and what your timeline is, they're not going to know how many staff to put on it to prepare, and you don't want that to be a hindrance in your process. And then it's important, it's a useful way to provide feedback in a non-formal sense from the NRC stance on possible issues with the design. And yeah, Chris?
Before you get to a company, like if a company is coming from pulling research from various universities or anything like that, is there potential to get involved in this kind of engagement ahead of time so that you can sort of license, or not license, but get feedback on specific technologies before you're trying to raise money to do all of it? Like, can you put some of that burden in an earlier process when you have less of a timeline-based system?
So, to a limited degree, yes. I think this part of the NRC activity is under their fee structure. So it's hard to get a lot of engagement, and I think you're not going to get any finality in any of those discussions before you get a specific applicant and a specific design. We've done work at Berkeley here on the FHR reactor, the solid fuel salt cooled reactor. We've been working on commercial design standards for those reactors. We've had NRC observers. They've provided some useful advice for that process, but I don't think that they're going to provide anything that's final.
So if you have NUP funding that covers something specific that might be cross-cutting when it comes to advanced reactor designs, like pebble fuel, that's not something that you would be able to use that money for?
You could theoretically propose that. I think it depends on NRC staff availability and resources. I think historically it's primarily been the DOE that's been funded to drive those interactions on advanced reactors. I'll talk a little bit about the NGMP experience. They had a lot of interaction with the NRC, and unfortunately, even with all of that, they didn't get very far in resolving issues. I will say my impression of the pre-application process is a lot of it is what the vendor applicant makes of it. I think I've seen varying levels of detail and varying levels of quality in the public presentations, at least, that are submitted by the vendors. My sense is that the more credible, the more well-developed, the more thought through the vendors' presentations are, the more valuable the feedback is going to be from the NRC. So this is essentially your time. You're paying for it, so it's important to know what you want to get out of it rather than just to do it for its own sake. one of the when I first got to Berkeley, this was actually pretty not so much before I first got here. So I was very interested in a lot of licensing processes associated with PBMR and followed a lot of their pre-application meetings and presentations. So PBMR, they went through a couple of pre-application meetings. They had a kind of an early false start in 2001 and then a much more intensive process in 2006. And then eventually they kind of partnered with Westinghouse to submit for one of the designs for NGMP before they kind of collapsed. But I think the point here is that PBMR went in, yeah.
Are you going to come to, because this question might be better later on, are you going to come to an international kind of perspective at all, or should I ask that question now?
I'm not really addressing an international perspective.
Okay.
I think that's coming up in part 2.
I'm going to address it.
Okay. I will say that I have one note here. The NRC is very aware. There's been a lot of public feedback, and they're kind of they're being proactive in trying to get information about how different stakeholders feel about the process. And part of that is looking at other regulatory systems. And so my impression, there's been good communication, at least with the Canadian regulator, on how different parts of the process can be improved earlier on in the process. But it's still not certain where that'll go. Yeah, PBMR was primarily South African in development. Westinghouse acquired a stake in it, and then ultimately did some development work on it to support NGMP, but then it folded. So I think the point, so the key point here on PBMR is that I can send links to the presentations if people are interested, where PBMR presented this information to NRC. They came in with a pretty high level of design detail on the plant. This is, I mean, you can't see here, but they had pretty detailed pipe routing in a lot of their auxiliary systems and support systems. They had a lot of detail, but they also had high-level issues that they needed to resolve. And I think part of the issue that I see was that the NRC issued a large number of requests for additional information based on the PBMR design, and they could actually go through a lot of detail and ask a lot of questions about specific systems, but those weren't the key issues to resolve. But I mean, they were interesting questions, but they weren't necessarily the ones that they needed to answer at that point. So they almost got themselves into too much trouble by trying to do too much too fast. And so they didn't really prioritize which issues needed to get resolved. Yeah.
So it's been 10 years, just curious.
So PBMR, in 2006, they went through a kind of, I would say, their most intense pre-application activity. In 2007, they submitted a lot of reports for the NGMP project through Westinghouse. And then I think 2010, their funding collapsed from the South African government, and they basically withdrew from NGMP. So it didn't go anywhere. But they did build large test facilities in South Africa, and it's a cousin of the Chinese HDGR program. They're both derived from the German pebble bed technology. So I think a lot of the insights and work developed have probably been incorporated to some degree in the Chinese program, although the Chinese program is largely independent. So it didn't, we don't see any PBMRs being built anywhere right now. So I guess it did not go well. So NGMP is kind of a continuation to some degree of PBMR. There are a lot of the same issues, also gas-cooled reactor, although NGMP was looking more broadly at different fuel forms, pebble bed and prismatic fuel forms. So the NGMP mission was defined by basically by congressional law, and the mission was basically to develop and build a prototype HDGR, and it had dual missions of hydrogen generation, process heat, and electricity. And I think there's a lot of really valuable work, and it's worth going back to look through some of the if there are questions that are interesting to you, it's worth looking back through the reporting that was generated for NGMP. It's kind of a good insight to see how this process works at large scale with a lot of people working on it. So I think the most important in terms of licensing was that after the development of a licensing strategy in 2008 to basically go through the licensing process with the NRC, DOE and INL, which were basically the actors of NGMP, submitted a series of 8 really important white papers to the NRC staff for review. And the real goal was to resolve a number of important policy issues. They were selection of events, source term containment requirements, and emergency planning requirements. And basically, the safety arguments for H2GR differ from those for light water reactors, mainly in terms of containment and containment function. So they were advocating what's referred to as functional containment. So it's really, you're deriving a lot of your containment function from the coated particle fuel. And what's unique about these reactors is that you don't actually care about the presence of the coolant to maintain safe conditions under accidents. So in their accident scenarios, their sequence event actually calls for the release of their coolant early on in the accident sequence, because that's before anything might escape from the fuel as the fuel temperature heats up. So it's very different thinking about a containment that's supposed to contain everything in versus a containment or a vented confinement. There's various different kind of linguistical tricks to get around it, but basically functional containment achieves the same function as containment, but doesn't do it with a leak-tight, large, solid structure. So in response to these white papers, there were about 25 public meetings, over 500 requests for additional information, that's RAIs. The Advisory Committee Reactor Safeguards, which is basically a panel of esteemed experts in reactor safety, not safeguards, but that's, they reviewed the staff assessment in 3 meetings, and basically the staff issued a preliminary review of the white papers, saying essentially that the approach was reasonable, there weren't any obvious reasons why it would be rejected, but there was so much uncertainty in what the Commission's policy would actually be that they failed to say that there would be any resolution on any of the major issues. So they put a lot of time, a lot of effort into doing this, and they basically didn't get anything. So this is a slide from Jim Kinsey, who was licensing director for NGMP. And basically, when they went into the process, they had expected that in the pre-licensing process, all the policy issues would be resolved early with small levels of investment. That would go into their final safety analysis report, and they'd move forward through the design process. In practice, though, they found that they weren't able to resolve any of the issues, and that ultimately uncertainty in policy and uncertainty in design meant that they had to get a lot further down the design path, a lot more investment in order to resolve any of those issues. And so these are numbers that are very discouraging to investors who are looking to develop new technologies, because you have to go very far down the path before you know if you're going to succeed or not. The third example I'll talk, so NuScale is working through this process right now. They're almost certainly the most likely to succeed through this pre-application process. They're expecting to submit their design certificate application this year. So in looking at the interactions with the NRC in the pre-application phase, NuScale has been very strategic in picking areas that they know are really important to resolve. They've presented, these are the issues as we see them, these are our strategies for dealing with them. We'd like your input on what you see as problems with our approach, and let's work to basically come to a resolution understanding of how we can develop an acceptable approach when we submit our license application. And so I think there are pretty much 4 major areas where they've been working. They're kind of general plant issues, control room operations for multi-module plants, the reactor building and reactor module approach. Again, a lot of this is around multi-unit plants. And then a lot of effort has been on their analysis and testing program. And they put a lot of effort into that early on. So I guess these are, this kind of relates to the question of what kind of policy issues. Go.
At which stage D&D goes into licensing, and also fuel cycle? Is that something that goes at this stage? Or?
You're saying defense in depth?
No, so it's UK dismantling, decommissioning, and also fuel cycle.
So decommissioning is not part of the license application. I don't think that there are any, so there are fuel handling components of the license application, but a reactor is my understanding is a different type of facility than a fuel cycle facility, and there's a different set of licensing requirements. I don't recall what section of 10 CFR they're under. When I made the point before that kind of pre-application, the process is pretty much what you make of it. NuScale has been trying to make a lot of it, and they've been very strategic in kind of saying these are the issues that we want answers to, and so they've been very explicit saying that these are detailed design questions where the current policy either doesn't apply or should be modified. Things like going into details of module assembly and equipment handling. So the current heavy load handling requirements isn't really adequate to reflect NuScale system because it doesn't include movement of modules that are loaded with fuel. So they've gone through a lot of the details of the regulations and identified the issues, and I think their chances of having a successful license application are probably a lot better because they've identified these issues, and at least they discussed their approaches with the NRC staff and gotten feedback on them. I should also make note that NuScale is also doing something innovative with respect to topical reports in the pre-application process. They're using this approach. So topical reports are often used for existing reactors to address generic issues that apply to many reactors. So NuScale is using these to get review and approval from the NRC on a number of different specific topics related to their own design. And they're doing this in a way so that they can go through and reference them and have approval on certain issues when they go through the design application submittal later on. And so this is their schedule. They're going to be producing a lot of these this year, if they this is a kind of a workaround for the fact that there's not a lot of ways of getting early feedback through the licensing process of whether something is acceptable or not. So they worked through this. I think it's important to note, it's not always the most exciting topics that need to go first. QA, the very first one, and they recognize that if you're not doing things under enough QA standards or to the proper level required to generate the data that you need, that invalidates a lot of their test program. And so they really, getting approval of that early on is important. And so it's details like this that I think NuScale has recognized and has done a good job of leveraging basically in the process. So I mentioned that the NRC is actually, I think, very receptive right now to a lot of the complaints of stakeholders that the process is very opaque and requires a lot of investment to get answers to even some very basic questions. So this is a slide, and this is from Deborah Jackson at the last NRC DOE licensing meeting. There have been two. It's kind of, they've gotten several hundred people each of these. It's kind of, it's been a good forum for dialogue between the NRC and kind of advanced reactor stakeholders. So the reference is there in the PDF. But so this is kind of looking at different parts of the process where the applicant can get feedback from the NRC on different parts of their design. And the notes here is that the NRC is currently looking at adding two parts of this process. One is a conceptual design assessment, and this is similar to a process that exists in the Canadian licensing framework. And also, I think a stage design review process is also possible under current statute. There's a provision in 10 CFR 52 that allows for different parts of the application to be reviewed independently. The main concern here is that if you submit a part and it's approved on its own, it doesn't necessarily guarantee you that when all the parts are submitted together, it'll be approved together. Also, if you have to go back and change significant portions of that part that's been approved, it will require additional re-review. And so it's not clear to me that actually the current regulations for a stage licensing approach actually would be all that helpful to an applicant. And so, how long might this process take? So these are notional timelines. These are not actual timelines, but they were generated by NRC staff as kind of rough estimates of how long things might take. And this is probably assuming everything goes well. So if you start now, basically you're looking at the mid-2030s to get any non-LWR built and operating. So this is kind of, I mean, I don't mean to be discouraging about the process, but this is kind of the reality that we face now. I think, let me go through and then I'll provide some kind of closing thoughts there. I'll talk a little bit about kind of just what's kind of happening now to reform the process and revise it. not to be too discouraging. So basically, as a result of these stakeholder requests, there have been these series of workshops, and the focus has been on using the existing licensing framework, but there's been an open dialogue about what kind of suggestions might come through. I think it's important to understand that the NRC is, like any other bureaucratic organization, it has to allocate resources to different tasks. If tasks are credible, and by credible I mean there's an actual customer pushing things through, that's probably the best path forward to getting something through more quickly. If it's just an early stage concept without a real commercial viability path, it's hard for the NRC to justify putting resources into addressing that technology. That's not what they view their role to be. But they are receptive to the fact that the process is opaque and that there needs to be more transparency and more feedback early on. There's also a process currently underway between the DOE and the NRC to develop technology-neutral advanced reactor design criteria. I'll talk about general design criteria coming up next. And they are developing technology-specific design criteria for sodium fast reactors and high-temperature gas-cooled reactors. So these are important steps in determining what the high-level safety requirements for design will be, and hopefully there'll be something that will have a high level of confidence that will be acceptable to the NRC if you follow those. I'll make a note that there have been a few kind of false starts on the long-term NRC goal to move more towards a performance-based, risk-informed licensing approach. I think 10 CFR 53 is kind of being reserved for this framework when it is eventually developed. Right now, there's nothing there. It's just being reserved. But I would use a note of caution here. One of the lessons from the adoption of 10 CFR 52 is that it can take a long time to be the first through a new licensing application. The current new LWRs are evolutionary from the plants that we know and have operated well, and it still takes 20 years to work through a new licensing process. So it's not necessarily a given that the performance-based, risk-informed approach will be faster for advanced reactors without the experience base, especially when you don't have reliability data on a lot of your components. So be careful what you wish for. It may be available, and the expectation may be to use it, but it might be that doing a two-part Part 50 license may actually be the most viable path forward for advanced reactors. All right. Any questions on the licensing? Okay. I'm going to move through a little bit quickly so I can get to kind of the case study, and I'll also work through a little bit of the safety design criteria, the general design criteria in those case studies, because you kind of bounce around a little bit from the ideas. Whatever reactor design you are working on, either in classes or professionally, it's really interesting to go through and think, how do these requirements affect my design, and do I comply? Is it important? Is there some reason, something that I need to do differently? And if you go to the NRC at some point and talk about safety, all of the safety requirements are derived basically from the GDCs. They're referenced extensively in any design application. They're generally divided into different categories. So there are general requirements, there are kind of fission product barriers, fluid systems containment, fuel and radioactivity control, and I'll work through some of them as in relation to kind of a few interesting questions later on. But these are the set of requirements that basically for light water reactors, if you can meet these, then the NRC will accept that you have a safe reactor. So safety classification of equipment is another actually important question. In the GDCs, the language is actually, they use important to safety rather than safety related. There's been clarification recently that these are the same thing. Safety classification is important because any SSCs that are deemed safety related will have special requirements in terms of sourcing, testing, quality, inspection. There's a whole set of additional things that you have to do for safety related components in the reactor. It also limits your ability to source products because the vendors have to be certified to basically follow all of those processes that are required for safety related. So reducing the number of safety related pieces of equipment in the plant is a good way to reduce cost of components. This is one of the things that Westinghouse makes arguments for in the AP1000. They've significantly reduced the number of safety-related pumps in their system by going to the passive containment cooling design. And there is, so I believe still untested, there is a risk-informed safety classification approach in 10 CFR 50.69. I can talk a little bit more about that if there's interest, but this framework exists, although it remains untested. So I'll talk a little bit now for the last 15 minutes or so about how regulations can impact the design process. This is motivated, or this is drawn mostly from work that I've done and other people in the thermohydraulics lab at Berkeley have done over the past 5 or 6 years on so this is the fluoride salt cooled high temperature reactor, or the FHR. It combines, I'm just going to give a little background on the technology in case people aren't familiar with it. But it takes two existing technologies from advanced reactors and essentially combines them, recognizing material compatibilities and performance that weren't known to people when they were doing the original concepts. So the FHR draws its fuel from the high temperature gas reactor world, the coated particle fuel, which has very robust fission product retention at very high temperatures. FHRs are using that along with fluoride salts as the coolant. FLIBE is the baseline design in most designs. It has excellent heat transfer properties. It has a very large volumetric heat capacity, so you don't have to pump very much of it around to move large amounts of heat. You can do natural circulation quite well for heat removal. We have students, the Berkeley students have been working on this for a long time, they're very good heat transfer fluids. We like them a lot. But it's kind of the combination of the robust fuel and the coolant that the logic is that it presents some very robust inherent safety characteristics for the reactor. It simplifies some of the operations versus a fluid fuel reactor. You don't have to handle all of the fission products in the salts. So we think that's an area of great simplicity. You get the solid fuel, which you need to account for. And essentially, compared to the gas reactors, you end up with a low pressure, high temperature system. So you can use thin walled components and draw from a lot of the high temperature design from the sodium fast reactor community, rather than looking at the thick walled, high pressure vessels of the gas reactor. So that's kind of why we think this technology is interesting, why we're studying it. Professor Per Peterson was one of the co-inventors of it back when he was working on the Gen 4 National Forum topics. So we developed a pre-conceptual design as part of an IRP, Integrated Research Project under the NEUP program. This was a team of graduate students, postdocs, and undergraduate students working through, basically, we wanted to get as much detail as we can in the nuclear island and the power conversion system. So this is the reactor unit. This is actually very similar to a combined cycle natural gas plant. That was one of the key questions, was if we could couple this reactor to essentially a combined cycle plant using external heating from the nuclear side. And so one of the things that we've done in this case, so these, let me go to the schematic. So here's the flow schematic. So here's our core, our reactor vessel. Our pumps are located in a hot well. The pumps are feeding two salt-to-air heat exchangers. The input from each one comes through the first compressor and the second one through the first turbine expansion stage, and then goes through and directly heats. So the key point here is that we have direct heating from the primary coolant of the reactor of the air in an open air cycle. So air is coming in, being heated, expanding in the turbine stages. We can actually co-fire natural gas, but then it's being vented back out into the air, essentially. It's a once-through process. So this is documented. There's a design report, but there was a question that Professor Peterson asked, and it provided a useful exercise of working through kind of different regulatory issues. So the question was, do these salt-to-air heat exchangers have to be safety related in terms of classification? I think the instinct of almost everyone is, of course they do. They contain primary coolant. They are single barrier for the open air power conversion cycle, of course they have to be safety related, but the question came up, and kind of I worked through a process, and it was I'll go kind of take you through that process now. But it's interesting because it shows you when you're thinking about the regulatory questions, you actually have flexibility in the design space, and you may end up looking at questions that you didn't expect to address in the first place. So that's the question: is it feasible to classify the air heaters as non-safety related? So then the question is, well, what actually does safety related mean, and what components have to be safety related based on the regulation? So there are a couple places, again, starting from 10 CFR 50 is a good place to go. It can be hard to figure out what section it is directly applicable. Definitions are usually a good place to start looking if you're trying to figure out what something is and what its requirements are. And then searching for terms that pop up in definitions is a good way to find good links. So 10 CFR 50.2 states that basic components must in all cases include safety-related design, analysis, inspection, testing, fabrication, replacement parts, or controls. So basically anything that's a basic component has to be safety-related. So what's a basic component? It's any SS system structure component required to assure integrity of the reactor coolant pressure boundary, capability to shut down the reactor, maintain a safe shutdown condition, and capability to prevent or mitigate. So the consequence of accident. So I'm pretty sure the cheetahs have nothing to do with shutting down the reactor in terms of neutronics. It's possible that they could play a role in decay heat removal, but we use a passive natural circulation direct cooling method for decay heat removal. So they're not necessary for decay heat removal. In that sense, they provide some redundancy. But they definitely are part of they contact the primary coolant, so this one's important. And because they are potentially a barrier, they are a potential important part of component. So then the question is, well, what safety functions might the air heaters perform in the Mark I? So decay heat removal, there are requirements in the GDCs to provide adequate decay heat removal. We've decided not to make them the component responsible for that. So they don't provide a safety function there. Pressure boundary, yeah, that's a big one, and containment function, that's a big one too. So let's go now to a definition of the pressure boundary. So pressure retaining components such as pressure vessels, piping, pumps, and valves. So that definitely includes components like heat exchangers that contact the primary coolant. But wait, there's a provision here for nuclear power reactors of direct cycle boiling water type. The reactor coolant system extends to and includes the outermost containment isolation valve. So at this point, there actually is regulatory precedent in a lot of reactors for components that are in contact with primary coolant that are not part of your primary coolant pressure boundary, and therefore are not subject to that requirement to be safety related. So it's not predetermined that it has to be safety related. It just depends on whether you can meet these requirements associated with isolation and containment. So containment functions are derived from the GDCs. GDC 16 basically requires a leak-tight barrier for containment to assure containment design components important safety are not exceeded. There's different proposed approaches through the advanced reactor design criteria. The NRC basically did not, in their review of the proposed ARDC, did not accept the language that was a little bit more flexible on the containment for the generic design, although there's more flexibility for the specific sodium and high temperature gas reactor designs. But these are the high level requirements. So kind of thinking about advanced reactors, we're looking at multiple barriers, control of radioactive release. So this is not a leak-tight containment. This allows for HTGR type of venting confinement scenarios, or for low pressure systems like sodium reactors, you could have different types of containment strategies. So this is what we proposed. There are various functions that we proposed for the different, the primary containment and the filter confinement. These are geared towards meeting the requirements specified in the GDCs. I'm going to skip over the details now. But it's important to note that there are other design options that one could have chosen. So Oak Ridge has developed a larger kind of 3,000 thermal scale FHR design. It uses different fuel form, and they actually chose to create a very large below-grade containment. And in this case, there's no primary piping going in and out of containment, only an intermediate loop going in and out of containment. So they made a different design choice to assess where their containment boundary should be. It's not for me to say necessarily which one is the correct approach. You just have different requirements for different systems depending on where they are. Defining where your containment is an important one, because access to containment is a very sensitive topic, both for operations and for security. There are different things that were prioritized. So in our case with the Mark I, we ended up with a compact containment below grade. We do have containment penetrations of the primary and secondary salts. There is water used to cool the outside of the cavity liner. We think that this provides some additional defense in depth for kind of beyond design basis, where you can add water to the system to provide additional cooling. In the HDR, they decided they didn't want any water inside containment. They didn't want any potential source of pressurization, so they just eliminated it by eliminating the material. Those are just different design decisions that one has to make when you're going through the process. So then the question is, well, if we're going to have penetrations of containment with primary coolant, what are the requirements for isolation? And this comes back again to GDC 55, which basically sets requirements for isolation valves for primary coolant penetrations of containment. And this is largely based on the BWR reactor experience. So I'll make a point here that there is kind of an out in the language of the GDC, which is basically saying you need isolation valves that meet some of these requirements, unless it can be demonstrated that containment isolation provisions are acceptable in some other defined basis. So given that language, there's actually wiggle room in the GDC. If you can make a compelling argument that's accepted, you can do something that's different from what's deterministically required in the GDC. But it's the burden of the designer to demonstrate to the NRC that there's no compromise in safety for that design choice, and that it meets the requirements. So essentially, all of these valve configurations require you to have one valve inside containment and one valve outside containment. And the goal is here to have redundancy and, to some extent, diversity in terms of location and ability to operate the valves. And the goal of ultimately being able to isolate the primary vessel and your emergency decay heat removal systems if you need to use them. So we developed an approach to isolating the reactor vessel. We don't have perfectly sealed valves that work in the salt systems. So we basically developed a concept of dams. They don't have to be leak-proof, but we think that they may provide enough isolation function to meet the requirements. We don't really know for sure, though. And there's also a secondary a gas gap system, basically, where we have a free surface to avoid anti-siphoning or to avoid siphoning from occurring. We think that this provides actually a diverse means of isolating the reactor core from any kind of transients that might happen from outside in the system. I think it's also important, so these were design decisions that we made. We don't know if these would be accepted, but we had to go through the process and figure out what kind of systems we would need to meet those design requirements. And it was a useful exercise to go through. I'll make a note as well that it's not always a given that the deterministic requirements are necessarily those that give you the highest safety. So I think as a reactor designer, it's imperative that you understand it's your responsibility to make sure that the system you're designing is safe, whether or not it meets the word of the existing regulations. It's your responsibility to design a system that's safe. So one of the interesting questions is in looking at the accident at Fukushima, so they had isolation valves inside and outside containments as BWRs were required to have. Basically with Unit 1, the isolation condenser started up, they were cooling, they actually were cooling more than they needed to, so they closed the isolation valves inside containment. They were unable to open the isolation valve inside containment when they lost power, and this probably accelerated the time to core melt to some degree. It probably would have happened anyway, but it's not necessarily that the configuration that those valves were in and their controllability wasn't necessarily the optimal configuration for safety under that station blackout condition. So it's really important for the designer to think through different scenarios and recognize what is the best way to achieve safety, and you have to do safety right and make your case to the NRC that you're doing safety right, because you're the one who knows the system better than anyone else. I think that's an important point there. So I'll wrap up here with some final thoughts on kind of a little bit of kind of this process. So some things that kind of became clear to me through working through kind of those questions, that the regulations that are applicable to any particular question are scattered in a lot of different sources. They're a lot more beyond just 10 CFR. It takes a knowledge of the landscape and detective work to basically figure out where you need to go. You also ask people who have experience. They can point you in the direction to figure out where you need to go. But sometimes sometimes it's good actually to have a prescriptive path forward that tells you what you need to do. It gives you a sense of a process. You may find problems with that, but it's very helpful if someone else has done it before. The regulatory issues can be interlinked in sometimes unexpected ways. A question about safety classification doesn't necessarily lead you to containment boundary definition, but they're all interrelated, and it's important to understand that there are trade-offs, and you make some design decisions for safety in some areas. It may have negative consequences in others, and you have to balance what you think is the best overall approach to safety. And then I said, ultimately, it's the responsibility of the reactor designer to develop a system that's safe and can meet both your top-level regulatory requirements to the regulator, but also there are other stakeholders. You're not designing a reactor for the NRC. You're designing the reactor for other customers that has to meet the requirements of the NRC as one stakeholder in that process. So, thank you, and happy to take any questions.